Okay, let's start. So this is week 9. I actually had a look at your midterms. I'll pass it to you on Friday. Um, um, yeah, we can discuss on Friday. Okay. But yeah. Okay. So so this is week 9. So what we'll do is I will first complete uh, the discussion on network flows. I'm not I've almost completed it. I need about half an hour to just complete a few more points. Um, and then we will spend this week primarily, I want to just discuss a couple of other algorithms for linear programming. I will give you the key ideas of the ellipsoid method and the interior point method. We won't cover it in as much detail as we did simplex, but it's important that I think you at least know what some of the key ideas in the methods are. And then what we'll do is next week, that will be week 10, I will start talking about discrete optimization. So we'll do sort of next week, I will do discrete optimization formulations. And then weeks 11 and 12, I will talk about methods for discrete optimization. And basically, week 13, I'll just keep it as, just for us to complete up the course, just review things, maybe things we have not covered and so on. Okay. So just to give you a heads up where we are. Okay. Okay. So let's first recollect what we were doing last class. So okay, so sorry, so let me just close up this and just open up the okay. So last class I basically told you. So recap. So I essentially discussed for minimum cost network flow problems. I essentially gave you the network simplex algorithm. Okay. So we spent majority of last class trying to concretize simplex for a minimum cost network for problems. So just to remind you what these problems were, you have a network on which there are some supply nodes and some demand nodes. So you might have supply on some nodes, and maybe you have demand in some other nodes, and you're trying to send, so there is supply, there is demand, and what you're trying to do is on this network, you're trying to send the flows to match supply and demand. So you're trying to send the supplies to the demand nodes at minimum cost. So what you have is on each arc, you have a flow xij, which is the flow, that's your decision variable. On every arc, I've got a cost cij, and I've got these supply nodes and demand nodes, which are given by these numbers bi. So we were basically solving this problem. We were trying to minimize C transpose X subject to AX equal to B, X non-negative. This was an uncapacitated version. If you have capacity constraints, you have upper bounds on this. Okay. And the key thing that we discussed last time was that the A matrix for network flows has this nice property. So it's called the incidence matrix for a network, and it's got some very nice properties. So, for example, because this captures flow conservation, that means the equality constraints here come from the fact that total inflow should be equal to total outflow at any node. This A matrix has this it's got this property which is called totally unimodular. So it's what's called a TU matrix. And this matrix has got very nice properties. It's got a +1, a -1 on each column. Everything else is zeros. And more importantly, it's got this property called that the matrix, basically the inverse of any, I mean, the determinant of any submatrix, square submatrix is either -1, plus, or 0. And so you can actually show that as long as the input here is integer, like B is integer, the optimal flows will always be integer. So it's a problem where if you have integer data, you automatically get integer optimal solutions. And this is not true in general for linear programming. For linear programming, you might have integer entries in A and B, but it doesn't mean that your solution has to be integer. I mean, the simplest is if I give you a condition like 3x equal to 2, 3 is integer, x 2 is integer, but clearly x is not integer, x is 2 by 3. Okay, so you're not guaranteed to have integer entries for x just because A and B are integers. Okay, but it turns out in this problem it is very nice. So in this problem you basically get integer optimal solutions if the data is integer. okay, is integer valued. And this is nice because though you may not plan for solving an integer program, you actually get an integer solution. Okay, and there are only some linear programs which have this property, and we will see this more when we talk about discrete optimization. We'll see more of this stuff. Okay, okay. So this was a recap from last class, and what I've started doing was max flow min cut. So I want to complete that duality idea there because I told you what the max flow min cut formulations are, but I didn't sort of complete the connection between the two formulations. Okay, so let me just remind you what's so one specific example of min cost flow is max flow min cut. Okay, so what is a max flow min cut problem? Okay, so let me just first tell you what the formulation is. So max flow is a problem where you have to solve the following problem. You are given a network and you have got a supply of V, which you're trying to figure out. You're trying to maximize V on a network where everywhere on this network, you've got capacities on links. Okay. So you've got capacities which are given by numbers Uij. And so what you're trying to do is you're trying to solve the following problem. I want to maximize V so that at any node, so I'm writing this from again, I'm writing flow conservation again. Essentially, if I is a supply node, which is, so if it is S, the node S, then it's the total outflow is total inflow, which is V. It's minus V at the sink node. If I is equal to T, and then zero otherwise, and then you have these constraints saying Xij between 0 and Uij, where every edge is in this graph has got a capacity Uij. Okay, so this was a max flow problem. This is an example of the min cost flow problem because you can rewrite this as, I mean, these are essentially flow conservation constraints, and you've got a lower bound of 0 and an upper bound of U. Okay, and you're trying to maximize flows here. That's fine. Okay, okay. So this is an example, and the dual of this problem. So this is an LP clearly. The dual of this problem was the following. So this is a primal. Okay, the dual formulation, which we are going to interpret as min cut, is the following. I want to minimize y. So there's a so I will have a sorry. My dual variables. There's a dual for every capacity for every arc, and there's a dual for every node. So for every arc, there's a, let's call this a variable Zij. So my dual is minimize summation over every arc in the graph Uij, which is a data, times Zij, subject to my capacity, my constraints. So for every node I into j, Xij shows up with a, so there is a Yi here and there's a Yj here. Okay. So for node I, Xij will show up with a positive sign, that'll be a +1. So I'll get a Yi. For node j, Xij will show up with a negative sign because that's an incoming arc. So I'll get Yi minus Yj if you write the dual carefully. Because Xij's they have no the arcs have no costs, the objective contribution is 0. So Yi minus Yj will be basically 0 because Xij is non-negative. This should be greater than or equal to 0. And then the other constraint, so this for every arc in the graph, except for this V, where you will get so there'll be a minus ys plus yt. So there'll be a constraint saying yt minus ys equal to 1. That's my dual. Okay. So this is my dual formulation. Okay. Again, we did this last class. Okay. So can I check if you remember this formulation from last class? Yes? Okay. So my claim is that, or what we are going to argue is that this actually is a min cut problem. Okay, so what is a min cut problem? The min cut problem, if you remember, is in the same network. If I give you a set of nodes, and let's say this is node S and this is node T, a min cut is in a given graph, if I've got edges going in whatever way, a cut is a partition of this graph into a set of nodes. So these are, let's call this node S. Let's call this node S bar, which is V naught in S, where the node small s is contained in this set capital S, and the node T is contained in this node is the set S bar. So what's a cut? A cut is simply a cut capacity is simply the cut capacity. A cut capacity is what? It's simply for any so cut capacity for sort of S comma S bar is simply the sum of the capacities when I lies in S, the set capital S, J lies in S bar, and Ij is an edge in the graph. So for example, this is a forward going arc that contributes a positive flow. This is a backward going arc. It goes from S bar to S. Okay, so it's not a forward going arc. So you're trying to send flow from S to S bar. So the capacities here will be basically the cut capacity for this will be this flow plus this flow, the sum of these two capacities. Okay, and so you try to check for every. So what is the min cut problem? The min cut problem is find the min FT cut is find the minimum cost, find the min cut capacity in this graph. Okay, and the claim is sending maximum flow is the same as finding the minimum cut in this graph. Okay, and what I showed you last time was, last time I claimed that if you take the optimal value of the primal, it has to be equal to the optimal value of the dual. Why? LP duality. Okay, strong duality. So I give you a primal problem, I give you a dual problem. If I write the primal and duals correctly, these two optimal values are the same, strong duality. Okay, so these two are, so this is strong duality of LPs. What I claimed last time was this is less than equal to, and I think in my notes I've got in my lecture notes I put the inequality the wrong way. This is less than equal to the minimum value of the FT cut. I argued this last time. Why is this the case? If you take the dual formulation, I'll argue why this is the case. And we showed this actually a couple of ways last time, but I'll just quickly remind you, why is this true? The idea is simply, one way you can think about this is just create for me a dual feasible solution and argue that every ST cut is a dual feasible solution. If every ST cut is a dual feasible solution and the objective gives me the cut capacity, because they are feasible solutions to my dual, and my dual is a minimization problem, my optimal value will be below the minimum ST cut value. Okay, and how did we see this? The argument was why? This because why was this the case? Set yi to be 1 for every node in S bar. So take a cut S comma capital S bar, set yi to be 1 for every node in the set S bar, and yi to be 0 for every node in the set S. Okay, where of course an ST cut means the set capital S has to contain small s, the node small s, and the node set S bar has to contain the node small t. So clearly yt will be 1, ys will be 0. It satisfies this condition. And what we and set zij to be 1 if ij is in the cut and 0 otherwise. So for example, if this was my set S, these two nodes, and S bar was the set, what this says is make these two 0, 0, make this 1, 1, 1 0, 0 yi's, make this 1, 1, 1, and set the zij's to be 1 for these two edges, and everything else make them equal to 0. Okay, and this will be basically dual feasible. Why? Because 0 minus 1 plus 1. I'm sorry, I think I made a. I missed something here in the. I missed something in the dual. The dual doesn't look right. So remember, in this dual, so I missed out something. The dual I missed out is xij as yj, but xij also involves zij. Okay, so the dual was not written correctly. There should be a plus zij greater than equal to 0. Okay. I mean, you have seen something is incorrect because z's were not showing up in my constraints. Okay. So there's a constraint here plus zij. So I missed the plus zij in my dual. I mean, this is linking up the y's and the z variables. Otherwise, of course, the problem is not interesting and not correct. Okay. So the idea is, for example, 0 minus 1 plus 1. 0 minus 1 plus 1 is equal to 0, is equal to 0. So it's feasible, and we checked this last time. Okay. So all this is from last week. Okay. Any questions before I proceed? The argument is going to be, in fact, this is not an inequality, or it's not less than equal to. The result is much stronger. It's actually an equality. This is a claim. That is, actually, this is exactly min cut. It's not an upper, it's not a lower bound on the min cut value, it's precise. So how do I prove this? So to prove this, we have shown it's less than equal to. So the natural idea is to prove that it's greater than equal to. If I prove a lower bound of the min cut value, or if I prove that I can find a ST cut, which is less than equal to this number, and this is the minimum ST cut, everything has to be equal. Right? So I just have to prove somehow that there is a lower bound here of a cut capacity. Okay, so we're going to try to argue this part now. Okay, and I'm going to use a slightly different argument. I just want to show you some other ways you can prove things. We will try to prove this using some randomization ideas, something about using some probability ideas, just to show you that you can intermix techniques when you think about optimization. Okay, so I want to show you something using randomization. Okay, okay. So we want to argue somehow this is equality. Okay, okay. So we'll first massage the dual a little bit, make it simpler. Okay. So is it clear where we are going? Are there any questions before I proceed? Okay. So first, we are going to simplify the dual a bit. Okay. Just to make it easier to deal with. Okay. This can be, so let's look at the dual. A dual was, so let me just cut and paste it. This was my dual. Okay, I'm not going to, this was my dual. Okay. Now there are two types of variables. There are variables which are on the nodes and variables which are on the edges. Okay. And observe that, sorry, I also had Zij to be non-negative. Huh? I also missed that constraint. Because Xij, so remember, Zij has to be non-negative in this formulation because Xij is less than equal to, sorry, I didn't write my dual carefully. Okay. Xij is below Uij, so the Zij variables will have a sign restriction. Okay. So this is a precise dual. Okay. Okay. So think about Zij. Essentially, the variable Zij occurs in two constraints. There's a non-negativity condition, and there is a one constraint for every arc. So what does Zij satisfy? Zij is greater than equal to Yj minus Yi, and Zij is greater than equal to 0. The two conditions. Okay. So remember, we are solving a capacity, a max flow. So this problem is interesting. All the uij's are non-negative numbers. Their capacities on arcs. My flow lies between 0 and uij. Okay. So all these numbers are non-negative. Okay. So I'm trying to minimize some non-negative combination of zij's. Zij has two lower bounds. So what should the optimal zij be? It should be the larger of these two numbers. I'm trying to put zij as small as possible. I have to be, if z has to be greater than 5 and greater than 7, and I'm trying to minimize z, make z 7. If I have to satisfy both conditions. So the optimal zij has to be the maximum of 0 and yj minus yi. Agree? Is that clear? Okay. So I can project out the zij variables. Of course, this is not a linear constraint. It's a piecewise linear convex function, but I can do this. Okay. So I can rewrite the dual as minimize summation ij in E, uij, zij. Okay. By the way, there's a representation. Maybe I should write it down here. You can define this as yj minus yi positive part. Okay. So I don't know if I've introduced this notation before, where I define a variable like x plus to be the max of 0 comma x. Okay. This is a very useful function. In machine learning, this is called the ReLU, the rectified linear unit. This is the simplest. It's a function which looks like this. It's a very useful function. It shows up in all type of problems like Nussbender problems. It shows up everywhere. Okay, these type of functions. Okay, so it's the simplest sort of the most interesting piecewise. I mean, the simplest extension of a linear function to a piecewise linear convex function. Okay. Okay. So I'm just going to use this notation. You'll see this a lot in papers. Okay. Okay. So this is yj minus yi plus subject to now because this condition now I've satisfied it with this variable with this choice. So my only constraint here is yt minus ys is equal to 1 for every I'm sorry, that's all. Okay. So next I claim I look at the problem and I observe that every variable shows up as a difference. Either that is yi minus yj or yk minus yl. The constraint is also yt minus ys. So if what matters to me is difference of variables, not the exact variable value. So I've got a degree of freedom here, okay, which means I can set one of them to be a fixed number. Okay, if I'm just having an optimization problem just involving difference of variables, then one of the variables can be arbitrarily set because I can always translate all my variables by a constant and keep my objective to be the same, right? If I take a solution y and if I transform this to y plus a constant delta where e is a vector of all ones, the difference between any two coordinates here will be the same. yi minus yj, this will be yi plus delta minus yj minus delta. Okay. So without loss of generality, we can set one of the variables to be fixed. So let's set ys to be 0. If I set ys to be 0, automatically my yt is fixed. Okay. Because of the constraint. Okay. So I can write my dual as minimizing summation ij in E, uij, yj minus yi plus, where I force now ys to be 0 and yt to be 1. Agree it's the same, the dual or no? Yes or no? You all are looking a little bit, not shaking your heads. So I don't know if I can. Yes or no? Sorry? Yes. Yeah. So the optimal objective value will be the same. If you translate every variable decision variable, you just translate by a constant It satisfies the constraints, the objective stays the same. Why does the objective stay the same? I'm taking difference of two numbers only. It's a function of difference of two numbers, right? Everything involves difference of two things. And I've got many of these variables. So one of them I can set arbitrarily. There's a degree of freedom. Okay? Is that okay? Okay. So hopefully that's okay. Now, next I claim in the optimal solution, all okay, this is only about ys and yt, but there's a y variable for every node. I claim that all yi can be set to 0 or 1 basically. Okay. Each yi. That means in the optimal solution for this problem, I claim that the y's have, if I restrict y's to be 0 or 1 binary values, that is no loss of generality. Okay. This is not as clear because firstly, y is general. No, y can be any number. It's any real number. This is some convex function. Okay. So we need to argue this. Okay. Why? Okay. So let's think about what can happen. Okay. So I claim that given any y, so any y, we can set y star to be, we can set y star to be the minimum. So I'll just show this to you. Minimum of okay. Okay, so we are trying to minimize. Okay, so I claim that if I give you any y, okay, which of course where ys is 0 and yt is 1, okay, I claim that if you actually transform the y's in the following way, what this is doing is, if y is, I'll tell you what this is doing. Okay, all this is doing is, suppose you're between 0 and 1. Okay, if y is, let's say if yi is some number which is greater than 1. If yi is greater than 1, what this is doing is it's moving yi back to 1. Because if yi is greater than 1, max of 0 and something bigger than 1 is that positive number. I take the minimum of that and 1. So it's moving it back here. If it's below, if yi is below 0, what is this doing? If yi is here, for example, it's maximum of 0 and some negative number, that's 0. The minimum of 0 and 1, that's 0. So it's basically for points which are outside 0 and 1, it's moving it back to the boundary points. For points inside, it's just going to keep it as is. So this is yi star, this is yi star. For this case, yi is yi star because here y lies between 0 and 1. So max of 0 and some positive number is the positive number, but that positive number is below 1. So minimum of that and 1 is simply here. Okay. So all this is doing, all this operation is doing is, if the number is beyond 1, moves it back to 1, below 0, move it to 0, in between 0 and 1, keep it. I claim that this will always make the objective function only, cannot make it worse, can make it better. Why? Okay. Think about what are some possibilities. Okay. So for example, let's say yj is here. Let's say yi is here. Oh, actually, let's make, yeah. Okay. If you look at the objective function here, there is a positive contribution to the objective only when yj exceeds yi. Okay. Otherwise, if yj is below yi, the contribution is 0 to the objective. Okay. So let's think of the cases when yj exceeds yi. So let's say this is yj. Let's say this is yi. This is 0, 1. So what is the contribution to the objective? Yj minus yi. If I move yj back to this number, I will get a number yj star, which is 1, minus yi. The difference this difference is smaller than this difference. So I'm only decreasing my objective function value by doing this. I'm trying to minimize. Huh? I have no interest in making things large. I'm trying to make things small here in the optimal solution. You can argue this similarly for every case. Okay. So, for example, if 0 and 1 is here, let's say my yj is here, let's say yi is here, what do I do? This is my difference yj minus yi. But I've got incentive to move yi to yi star, decreasing yj minus yi star. This makes yj minus yi star here will be lesser than yj minus yi. So if I've got a negative value, by decreasing it, I'm only making my difference smaller. If my numbers are within 0 and 1, it doesn't matter. I just keep them as is. Okay. And you can go through this case by case and check this basically. Okay. So hopefully you're convinced that somehow there is no benefit for you to make these numbers go beyond 0 and 1. Okay. You're convinced or no? Okay. Okay. So we are almost there. Okay. So dual. Okay. So the claim is that when we solve this dual, the optimal. Okay. So I already told you what the optimal dual are. Okay. The variables are. Okay. So now take an optimal take an optimal solution to the dual. Okay. Of this form. Every yi will there are numbers for nodes. They lie between 0 and 1. Okay. Ys was set to be 0. Yt was set to be 1. This is the optimal solution. And then I've got a set of y values for every node which lies between 0 and 1, because I've just argued that every value here will lie between 0 and 1. So I'll get an ordering from the optimal solution. Okay. So I might get, for example, if I might have yi, let's say here, maybe I've got yj here. Okay. And let's say ij is an edge in my graph. Maybe I've got yk here and yl here. Okay. So for example, in this graph, I might have a node which goes from I to j, and I might have a node which goes arc which goes from k to l. Okay. I mean, I don't know what the relationship between yi and yj is, but let's say, for example, there is an arc going from I to j. This is a forward arc. Or if there's an arc going from k to l, but yk is greater than yl. So there are some forward arcs and there are some backward arcs. Okay, in this, based on I have the dual variables. I just create this graph. Okay, my contribution to the objective, my contribution to my dual objective are only from my forward arcs. Okay, why? Because my contribution is what? From yj minus yi, positive part, yk minus, in this case, because yk is exceeding yl, essentially you think about these are edges going from I to j. Okay. So this is an edge. But in this example, it should be what? The contribution could be yl minus, so this is from I to j. So this should be, yeah. So this will contribute a positive part. Okay. But this will not contribute because this should be yl minus yk positive, right? So only the forward arcs will contribute in the edge. I mean, my graph has edges. Whichever nodes, wherever this dual variable or this y variable is larger than this variable, it will contribute. Okay. Otherwise, it won't. Okay. Sorry, where yj exceeds yi will contribute, but your yl is less than yk, it won't contribute. Okay. So this number should be larger than this number. Okay. Okay. So only forward arcs contribute. Okay. So now let's do, so now we will create a cut. Okay. But we are going to create a cut in a random manner. Okay. Now we are going to create a random FT cut. So this is where sometimes probabilistic thinking helps. Okay. Sometimes the use of probability is a very useful tool for doing analysis of algorithms. Okay. This is a very useful technique in many areas of optimization. I want to show it to how to do it in this example. Okay. How do we create a random ST cut? Do it in the following way. Okay. For any number u between 0 and 1, strictly between, so it can be up to 0, but let's keep 1, so it's strictly below 1. Okay. Define the set S of u as what? All nodes in the graph where yi star is below u. Okay. So for example, if my u was this, suppose I pick this number u, these two nodes and this node S will be in the set S of u. These three nodes will be in the set, will not lie in the set. But if I chose, for example, the u to be this number, all these nodes will lie in the set S of u. This will not lie in the set. Okay. Clearly, the source node lies in S of u, and T does not lie in S of u for all u between 0 and strictly less than 1. Okay. This by almost by definition, because yi star is 0, yt star is 1. So this, so therefore, S of u and S bar of u, which are basically nodes which lie in the vertex but don't lie in the set, define a FT cut for all u. Is it clear what I'm doing, construction, or no? Is the construction clear? As I change u, so for any u, I will define an ST cut. If my u was chosen here, my ST cut would simply have the node small s. That's a ST cut which might just involve, for example, so just a cut like this. If my u is very large, my ST cut would simply be all the nodes will lie on this side and only T will lie on the other side. So I can create all type of cuts as I change u, basically. It depends on what my dual variable values are. Okay. Okay. So as I change u, I'm creating different ST cuts. Okay. Think of creating u randomly. Okay. So let u be generated uniform random in 0, 1. Okay. So generate a uniform random variable between 0, 1. This you should remember from your basic probability class, your first probability class. Between 0 and 1, you generate the density function will the density function will look like 1. Essentially, it means every value between 0 and 1 is chosen with equal probability. Okay. It's a continuous variable. Okay. So if I generate u randomly, I'm generating random cuts. So I will look at, so this generates random FT cuts. Okay. Let's look at what the random cut, what is the behavior of the random cut? Okay. So what is the probability that a link ij, an edge ij, lies in a random cut this S of u and S of u. Okay, I'm going to use tilde for randomness. Okay. So I'm generating u randomly. So a link might be on a cut or not on a cut as u changes, right? So what is the probability? The probability is simply, it will be part of the ST cut if u, so for example, the value u for, let's say, take the link ij, the value u has to lie between these 2 points. If u lies on this side, both of these nodes I and j are on one side of the cut. If U lies on this side, both of these on the other side of the cut. Okay. And if the if the arc KL goes in this way, it can never be part of the cut. Even if U lies here, this is a backward arc in the cut. So my only chance is when U lies between these two numbers, okay? So which means that it's a probability that this number U exceeds yi star. I'm sorry, U is, uh, so yi star is below U. Yi star is below U, which is below yj star. Okay. And everything is continuous variable. So this, strictly less than equal to, strict less than equal to, or strictly less than do not matter. They're all zero probability events, basically. Okay. So what is this probability of this? It's simply yj star minus yi star, the positive part. Okay. If the link, if it was something like this, so this is simply the positive part. This only happens if yj exceeds yi. Okay. Higher, whatever is the length of this interval defines the probability of this happening. Is that clear? No, it's not clear. So what is the probability that a random cut, that this edge will be part of the random cut? If U was here, these nodes will be on one side of the cut. It cannot contribute to the cut capacity. If U was here, these two nodes will be in the S side of the cut. They will not contribute to cut capacity. They only contribute to the cut capacity when I is on one side and J is on the other side of the cut. When does that happen? When U lies between in this interval. What is the probability that U will lie in this interval? The probability of U lying in any interval, let's say a uniform random variable, the probability of a uniform random variable taking numbers between 0.2 and 0.3 is 0.1. It's an equal probability event, right? This is probability. This is just the definition of a uniform probability. What's the probability of a random variable lying between A and B? Is B minus A. So what's the probability of it lying between yj and yi? Yj minus yi. The positive part here is simply if, for example, it's a backward arc. So U could have been here, but this cannot contribute to cut capacity because there's a backward arc. So whenever y, it can only contribute if yj exceeds yi, basically. Right? Backward arcs do not contribute to cut capacities. Okay, so this positive part is simply to keep track of it's a forward going arc. I is on one side, J is on the other side. This is part of S, this is part of S bar, and this cut is going this way. Okay. Okay. So what is now the expected cut capacity? What is this? You take every edge in the graph. Uij is the cut, is the capacity. What is the probability that ij lies in this random cut? But we just found this. It's exactly Uij, it's exactly Yj star minus Yi star plus positive part. But now we are almost done because this is exactly the optimal value of the dual. Okay? Because this is exactly what the dual was. When you simplify the dual, this was the dual formulation. Okay? So what have we shown? We have shown optimal value of primal, which is max flow, which is equal to optimal value of dual. This is strong duality for LP. We have shown this is lesser than equal to minimum FT cut. But now we have just shown that this cut capacity, expected cut capacity, which is the ST is the optimal value of the dual. This is exactly in expectation expected FT cut capacity. If a random variable in expectation, how can, I mean, how can I have, sorry, how can I, so this is an expected cut capacity. Every cut capacity has to be lesser than the minimum ST cut. So the only way this can occur is these two have to be the same, right? There's no other way this can occur otherwise. I cannot have a random variable below some minimum number. It only takes, because the smallest value is an upper bound on this number. I'm taking an expectation over this. So this has to be the same, right? So therefore, equality is there throughout, holds throughout. And because this is max flow is equal to min cut. This is exactly max flow. This is min cut. Equality holds. Max flow is equal to min cut. Okay, this is one of the most important duality results in network flows. Okay, it's basically LP duality but concretized to the network setting. Okay, so again, I don't know if this last part was clear to you, but the idea is that I'm generating many cuts. The average value of this cut is equal to the optimal value of the dual, but the dual value cannot be larger than the smallest possible cut value. Okay, this expectation means what? It's probability times some cut capacity. So if I've got a random variable which is always below every realization, and the expectation is the same. If I tell you a random variable, let's say a random variable is below 3, let's say, okay, every realization of the random variable is below 3. And I tell you that the expected value of this random variable is 3. How can this happen? Only if the random variable takes only value 3. There's no other way. If the random variable takes a value which is below 3, in expectation, it has to go below 3 because there's some probability of this happening. So the only way this can occur is the random variable should take a value 3. Okay. Otherwise, it's a zero probability event which cannot compute, which cannot contribute basically. It can only take value 3 with probability 1. There's no other way basically. Okay. Okay. So I just wanted to show you that sometimes you can use randomization to your advantage. Okay. Again, this is a useful thing to know for optimizers. Randomization is a tool. It's a very useful tool for probabilistic arguments. And there's an entire area called probabilistic combinatorics where you can use randomization to your advantage for thinking. I've just given you one example. There are many more examples out there. Okay. Okay, any questions here? This is a very important result. So basically by solving the min cut the LP dual, we get the min cut problem. Yeah. Yes, it will be, in fact, the min ST cut will become exactly, so this will become equal. The minimum ST cut, so what is this telling me? It's telling me it's going to give me a cut. Okay, I'm not telling you what the cut is. Okay, some cut. So for example, let's take an example maybe. Let's take a graph like this. Let me just keep it a bit simple. I think I did this last time, this example, right? If I remember correctly, I gave some numbers here. Let me just create the example. The capacities here are 3, 2, 1, 1, and 3. Okay. Max flow on this graph is actually 4. Okay. So these are capacities. Okay. Okay. I claim you cannot send more than 4 units of flow. So you can send, for example, 5 units from here. You could have sent 5 units. It's allowed here. But this cut is going to force you, because I cannot, only 4 units can enter here. So if I send 5 here, something has to happen with that 1 unit. I don't know what to do. I cannot send it out anywhere. Okay. So the max flow in this graph is 4. Basically, you have to send, I guess you have to send 1 unit. The flow will be 1 on this link, 2 on this link, 2 on this link, 1 on this link, So 2, 1, 1, 2, 2 plus 1, 3, 3 on this link. Okay. What is the min cut in this graph? And there are actually two min cuts in this graph. So one min cut is, so this is not a min cut. The cut capacity of this is 5. But this is a min cut. If you take this cut is what? Essentially the nodes, if I call this node 1, let's maybe there's too many, A, B, C, and D. This cut has got A, B, C on one side and D on the other side. Okay, it's partitioning, right? What is the cut capacity? 1 plus 3, 4. So cut capacity is 4, which is exactly max flow. If you take this 3 plus 2, 5, that's a cut capacity of 5. That's not a min cut. And I claim you cannot do smaller than this. There is actually one other cut, there's another optimal cut, which is actually this cut. Even AB and CD, this has got a cut capacity of 1, 1, and 2. It's also cut capacity 4. So there are multiple optimum in the dual. Okay. The corresponding yi and yj values will be, yi will be like this will be, so for this, let's say for this capacity ABCD, this will be a value of 1, the dual variable. This will be a value of 0, 0, 0. Zijs will be 1 for this and for this. The point is, when I look at this, it's not beforehand clear that the optimal values have to be 0, 1. It's not clear because you're solving an LP. So I had to go through some arguments to argue why the optimal solution is binary. Though we didn't, like I didn't, I mean, the point is we don't want to solve it potentially as a binary optimization problem. We're solving LPs. LPs, we have efficient algorithms. Okay. Okay. So I just want to make one more, so we'll take a break, but I just want to make one more, I just want to point out one more thing about shortest paths before we end this discussion. So for shortest path problems, okay. So remember what shortest path problems are. We're trying to minimize summation Cij, Xij. So it's a shortest path problem where you've got inflow so again this is flow conservation. 1 if you're source node, -1 if you're a sink node, 0 otherwise, where Xij is non-negative for every ij in E. Okay. So it turns out so what is shortest path problem? You've got a node S, you've got a node T, you're trying to send 1 unit of flow with of minimum cost in this graph. Okay. Now it turns out shortest path is solvable as an optimization problem of this type when all the Cijs are non-negative. Okay. So one of the things which can happen in shortest path problems is you can have cycles. Okay. So if shortest path is solvable as a LP. Okay. So this is a linear program. If you solve this problem, you send 1 unit of flow, it might send 1 year, and it sends it out here. But this is only when the costs are non-negative. Shortest path, if you have negative costs, can be a tricky problem. Okay. In fact, it's an NPR problem. It's a hard problem because you can have cycles. Okay. So here's an example. Let's say I've got a graph like this. So what does negative cost? What problem can it cause? Okay. Let's say I've got a graph. Let's say all my costs are 1. So these are all costs. Okay. Okay. This is my source node. This is my sink node. I'm trying to send 1 unit of flow, 1 unit of flow. Okay. So what is different in this graph? I've got a cycle. So there's a directed cycle. Okay. Let's call this maybe A, B, and C, these nodes. There's a directed cycle. Actually, let's make this number maybe Okay, let me just modify this number a bit. Let me make this -3 and let me make this 1. There's a directed cycle A, B, C, A. Okay. So let's say I'm trying to minimize cost. Okay, I'm trying to send 1 unit of flow from here to here. Okay. I'm trying to solve this LP. Okay. What do you think will happen? It will send 1 unit of flow. Okay. I can only send 1 unit of flow from here, right? So I cannot send more than 1 unit. 1 unit enters, 1 unit exits. Okay. 1 unit should enter here for flow conservation. Now, what you would expect to happen is you would expect 1 unit to flow here from A to B, and you will get a total cost of 3. Okay. What does a negative cost cycle do? I could have sent, instead of 1, this cycle is a negative cost cycle. I'm trying to minimize costs, which means if I go once around this cycle, what's my cost around the cycle? The cost around the cycle is 1 minus 3 plus 1, which is -1. That's attractive. I'm trying to minimize costs. So why don't I send 1 plus 1, 2 units here, send 1 unit here, send 1 unit here. This satisfies flow conservation. 1 coming here, 1 coming here, 2, 2 going here, 2 coming here, 1 going out, 1 going out. It satisfies flow conservation. Right? 1 coming, 1 going out. 2 coming, 2 going out. 2 coming, 2 going out. 1 coming, 1 going out. Works. But now let me be greedy. Let me not send 1 unit. Let me send m units here. Let me make this 1 plus m. Let me make this m. Let me make this m. And let m go to infinity. 1 plus m is equal to 1 plus m. 1 plus m equal to 1 plus m. Satisfies flow conservation. So what are you doing in this problem? You're basically not taking a path. You're in a directed cycle and you keep going on the cycle again and again and again and again because you're minimizing cost. Okay. It is not finding you a path, this problem. Okay. So it turns out when you have directed cycles, so cycles can cause an issue in shortest path problems if you have negative costs. Okay. So negative cost cycles are problematic for shortest path problems. And basically, it turns out you can't solve those problems in polynomial time efficiently. Okay. You can't solve it as an LP. Okay. So this idea of solving shortest path as a LP works whenever these costs are non-negative. Okay. Of course, if the costs are non-negative, by definition, this cannot happen, right? I can never have a cycle. Even if I've got a cycle, it's okay, right? If I've got a cycle, if my costs are non-negative, a cycle can only, I'm adding up costs. It can only be a positive number. Why would I take a cycle? So there's only an issue because there are negative costs here. Okay. So negative costs with directed cycles are an issue for shortest path. That's a hard problem. Okay. But if you don't have, if your costs are non-negative, no problems. Okay. You can solve it in polynomial time with NLP. Okay. Fine. We'll stop here. When we come back, I will introduce the ellipsoid method. Okay. So let's take a 5-minute break. Our speaker is decreased since January 26 onwards. So we will receive 3,000. Yes, I just received 3,100 or more, right? So much. So now when this one is in the time. So it's like people listen to songs that you like I do. So what is why again? Why I am like also so the final example is like how much is flowing between XIJ. Yeah, it's how much flow between two nodes. Yeah, but then the how much is like the capacity of one say
but then you take the tool, your YIJ, your YI and YJ is now about which one is in the source, which one is in the soup. Because now you want to see like, okay, instead of how much is I, which is the J, instead of saying how much is the J, you just see like cut here, where is this source and things. Yeah, so that's why you know your YI source, YJ is safe. Yeah. So that's why it's like now we only consider binary values on your variables, which is like either take 0 or 1. So that's why we talk about the 0, 1 thing. And then when you say that when you say that you're doing the uniformly randomizing where your card sends, my card can either be here or like either be here too. So if the card is here, that means your YJ is the other side. So when there's something like this one, S, and S is S is got like a left side word, and S bar is the right side word. So let's say that I randomly choose it like this. Then these two are real to the left side. So these two variables think so valid. But then all of the what's still big rather than 0, 1. But if I like randomly compare it, then this one will be 1, this one will be 0. For YI or YJ can have the value just be 0 or 1. Yeah, yeah. 0 or 1, whether it's on the left or right. I see. Yeah, so that's why he says now it's not about how much is so which way. It's about where I cut. Where you cut. Yeah. Yeah. So it's like, for those people, yeah. Yeah, then so the probably wouldn't be more than the more blue. What was it? Yeah, it's really hard to see it, because then I asked and I was like, oh, I think I also got really confused. So I had to like begin it. Because he was rushing through the play. It's really better. Really useful. Like, I also was like, I slept so late last night because the course ended at 10. Then they're showing. I just like, I'm just shelf this thing. And it was so bad. I was like, it's too much man. It's a bit publishing. It was against this rushing. You know, doing that. Like, excited. You was taking the bus. Oh, you were rushing. From that reason that you believe it's signature. This is the only thing that trail is just not really trees. It's like it's very flat. Like, is it really short? Right? You really use that. You're like, you're like, it's a lot of it. Really inspired. Second class teaching. It's also interesting. No, I don't know. It's interesting that we need to pay attention. Plus, it's really too big for them. Like, there's a process in this. Yeah,
Okay, so maybe we'll start. Uh, okay, so just to give you a heads up, we have basically finished about 7 chapters in the book. Okay, network flows is chapter 7 in the book. Um, there are the next 2 chapters in the book. Topic chapters 8 and 9 talk about ellipsoid and the interior point method. Okay, so so we are going to do these 2 chapters a little bit more, not as much in detail. Okay, the algorithms are different, but I do want to ensure that at least ideas of the algorithms are clear to you. Okay, the nitty gritty details take a lot of work to go through, and I'm not sure we are going to, you're going to get. I mean, we'll be able to cover it anyway in our time. Okay, so this is I want to give you a sense of what the ellipsoid and interior point methods are. I will probably spend the next 1 hour, whatever the next part of this class and next class, and I will try to cover as much as I can in this before I move to discrete optimization. Okay. So the question is, why do you require other algorithms for linear programming? So what do we know about LPs? Okay. So we know LPs can be solved with simplex. Okay. And we have I mean, you know exactly how to implement simplex. Okay. And it works in practice. It actually works very well in practice. Okay. Okay. Now the question is, so a question that the researchers were thinking about is, can this, okay, it works well in practice. Can you concretize this idea? What does it mean for something to work well, run efficiently? Okay. So it turns out that, and I will try to make some of these concepts a bit more clear today. Okay. Um, Sorry. Um, so it was unclear for many years if it always works well. Okay. So what this means is it works well empirically in many examples, but can you create an example where the method does not work well? Okay. And it turned out in LPs for the simplex method, you can do it. Okay. Namely, there exist worst case instances such that simplex takes an exponential number of iterations. Okay. And I will, we won't do the worst case instances, but it's there in the book, for example. So what does it mean? Okay, a worst case instance. So think about linear simplex. What does simplex do? Simplex takes a simplex takes some, let's say there's a polyhedron, okay, of some type. What simplex does is it starts off at a basic feasible solution, it moves to some new basic feasible solution, it moves to the extreme point, then it moves to some other extreme point. It does this every time, decreasing the cost in the minimization problem till it converges. Okay. Now, because it goes around the boundary of the polyhedron, the simplex method, it turns out the challenge in polyhedron is there can be many boundary, like, no, you can have the polyhedron can have extremely large number of boundary inequalities which define the boundaries. Okay. So it turns out for every instance of the simplex, in simplex you can play about with the entering variable, the exiting variable, you can use all type of rules. You can create an instance where it has to basically go through every basic feasible solution before it gets to the optimal solution. So you can create such instances. Okay. So it was not clear if you can create a version of simplex which can run in polynomial time but not in exponential time. Okay. And this was an open question for many years actually. So in 1979, a Russian mathematician, Kachian, showed LP can be solved in polynomial time. I'll make this precise what polynomial time means. Okay. Can be solved in polynomial time, but he could not do it with simplex. Okay. He had to use a different method in polynomial time using what is called the ellipsoid method. Okay, and I will try to tell you the method today. Now, the ellipsoid method, you might say, okay, if the ellipsoid method runs in polynomial time, let's just use that for in our algorithms, when we are running algorithms, why should I use simplex? Okay. It turns out the ellipsoid method is a good theoretical algorithm. It's not a particularly good practical algorithm. So theoretically, you can prove that it solves LPs in polynomial time, but practically it doesn't work. Okay, and I will try to explain that also. Later in 1983, building on some other work, Karmakar. Uh, okay, so but the ellipsoid method has some advantages which I'll explain later. Okay, so not practically efficient. The ellipsoid method. So later in 1983, Karmakar introduced what's called the interior point method. Okay, okay, in polynomial time, poly time, using interior point method. So again, there's a different method. Okay, this is tends to be both theoretically and practically efficient. Okay, uh, and I'll try to at least give you the idea of the algorithms. I won't be going through these algorithms in detail. Okay, we won't be going through it like simplex. Okay, but these algorithms use different ideas. Okay, they don't work with the simplex idea. They work with a different idea. So I want to explain those ideas. Okay, okay. So that's a bit of background. Essentially, for LPs, from what I, there are three main algorithms: simplex, ellipsoid, interior point. Recently, some people are looking at first order methods for it, but these are the main three algorithm classes for LPs. Okay. Okay. So we need to understand a little bit what it means to be. So I want to give you a little bit of understanding about computational complexity. How do you think about if a problem is easy, if a problem is hard? How do you try to analyze it? Okay. So what's an optimization problem? An optimization problem in general is you want to minimize C transpose X, let's say, subject to X in some set X. Okay. In fact, it should be minimum. Let's even keep this more general. Minimize f of x subject to x and x. Okay. I got two inputs here, f and the set x. Okay. When I say I've got an algorithm to solve an optimization problem, it should solve it for all the functions and for all the sets of the type x. Okay. Okay. So for LPs, we are looking at problems of this type, ax less than equal to b. So what's a problem instance? An instance of the problem is a particular matrix B, a particular vector B, I'm sorry, particular matrix A, a particular vector B, a particular vector C. Okay. Now, if I want to say that a problem, so this is a problem instance. I change A, B, and C, I get a different LP. I want an algorithm that can work for every problem instance. Okay. And I want it to run fully efficiently. So I need to first define, so we need to define the size of a problem. Okay. We need to define the size of a problem instance. Okay, how do you define the size? A size of a LP. Okay, 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 okay. So I require. So I'm just going to introduce one notation here, which would be sufficient for us, which is a big O notation. Okay. So what's a big O notation? This is a notation coming from asymptotic behavior of functions. Essentially, if I say, so this is a definition, I say f of n is some big O of g of n if where n is a non-negative number if there exists some constant m positive, non-negative, and some number n naught non-negative such that this function f of n in absolute value does not grows at most m of g of n m of g of n for all n greater than equal to n naught. Okay. So let me tell you what this definition says. So I'll give an example. But basically, it says this function f of n behaves like of the order of g of n if you increase n beyond some number. This f of n does not grow. It grows at most as a constant times this function g of n. Okay. So asymptotically, f of n cannot grow faster than g of n when n grows large enough. Okay. So for example, if I give you a function, let's say n cubed, 7n cubed minus 3n squared plus 2n plus 1. These numbers don't matter to me. 7 minus 3, 2, 1. What matters to me is this is a function which is the order of n cubed function. As n grows, the n cubed term will dominate everything else. Okay. Log of n grows. So if this is n, if this is a function n, log of n grows slower than n. Okay. So I can claim this function is of the order of, I can say order of n log n, but if you want, you can think of this as an order of n squared. So n log n is the tightest bound. Okay. But n log n does not grow faster than n. So this is a function which grows only polynomially in n. Okay. But if I've got something which behaves like 10 to the power 10 plus 5 n to the power 100 plus 3 to the power n. As n grows, what will be the most important term here? 3 to the power n will be the most important term. Okay. It doesn't matter if there's a 10 to the power 10 there. Okay. When n grows large enough, at some point, 3 to the power n will dominate everything else. So these two are polynomial growth functions. This is an exponential growth function. We want algorithms which can, in the size, so n should be the size of the problem input. We want running times which are polynomial if possible in the input size rather than exponential. Okay. Is that clear so far? Okay. So now let's think about, so what's a polytime algorithm? So definition. So an algorithm runs at polytime. An algorithm runs in polynomial time. I'm writing P as polynomial, it's a short form. Okay. If the worst case running time, worst case, in the worst running time over all problem instances of size n is of size n. Let's denote this running time by T of n. Grows polynomially in n. Okay. In other words, there exists some number k such that Tn is order n to the power k. I don't want k in any way to depend on n. Okay, so k is some fixed number. Okay, but I don't want this n to show up in the exponent in any way. Okay, fine. Okay, so for this, okay, so far clear? Okay, so size of LP. Okay, so let's think about the LP. Okay, so for LP size, the initial, the first, okay. So if you think about the LP, C is a vector in Rn, A is a matrix in R m by n. So I'm not using a standard form. You can do this with standard form. It's fine. Okay. It won't change. Okay. We are going to do everything only using the big O notation. So, so I've got essentially what? I've got m constraints, n variables. Okay. Okay. So if I increase the number of variables as n increases, my LP should grow in size because I have to keep track of more C's, more A, more columns of A. As my number of constraints increase, M increases, I keep track of more rows of A and more values of B. Okay, so clearly the size of an LP should grow in M and N. Okay, that's obvious, right? If I've got an LP with 100 variables and 500 constraints, as compared to 1,000 variables and 5,000 constraints, that's a much larger problem. The second problem. Okay, and it's growing. I'm storing as many numbers. Basically, how many entries am I storing? I'm storing roughly order M times N entries, right? It's N entries plus Mn plus M. But as a order, M times N entries have to store. Okay. If M grows, N grows, this grows in this form. Okay. So this is obvious. What is important next is how do we store the numbers A, B, and C? These have numbers in them. They're numbers, right? There's a 0.5, 25, 36, whatever. Okay. So the question is, each entry of the A, B, and C have to be stored. Okay. And now it comes down to how you store numbers on a computer. Okay. And how do you analyze the complexity of an algorithm? Okay. So the way you do this typically is we're going to assume that all the numbers that we are going to, the input of the LP are going to be either integer valued entries or rational valued entries. Okay. So we are going to assume, and this is how you do typical analysis, assume that the entries are integer or more generally rational valued. Okay. Why is this? To do analysis? Because if I tell you you have to work with my input to an LP, let's say it's square root 2 times something, you have to ask the question, how do you store square root of 2 in the computer? That's an irrational number. To store it, you need an infinite number of bits. Okay. So then you have to talk about how your errors in the numbers propagate and so on. Okay. So the way analysis is done is for algorithms is we're going to work with so we're going to think that our inputs to our numbers, I mean, rather than this, maybe we are going to input for the LP just 1.4142. That's fine. Okay. That's a rational number. Okay. 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 So let's think about how rational numbers are stored. Okay. So we're going to use, so how do you store integers? So to store, let's say to store an integer. So let's say I want to store an integer. Okay. Let's say R, which takes a number between 0 and let's say 2 to the power n bounded from above. Okay. How do I store an integer? So what we do so all computers, what they do is they use a binary representation. They take a binary representation of a number, use bits to represent numbers. Okay. We require essentially n bits. Okay. Example is the easiest way to see it. If I want to store numbers 0, 1, 2, 3, 4, 5, 6, 7, how do I store this as bits? I store 0. Suppose these are my 8 numbers I want to store. I will store 0 as 0, 0, 0, 1 as 0, 0, 1, 2 as 0, 1, 0. So think the value of this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So with 3 bits, I'm storing numbers going from 0 to 7. So in general, for an integer, okay, fine. So this is for positive numbers. Okay. What happens if you have negative numbers? You just add an extra bit. Okay. So if you have negative numbers, so for negative numbers, just add one extra bit. Okay. So I can have an extra bit here, which is positive or negative. So if I want to have the number, if I want to have the number 0 to 1, maybe I keep all of this as 1. But if I want it to be 0 to -7, I simply make this 0, 0, 0. So I just throw one extra bit. one bit which will tell me if it is positive or a negative number. That's a binary number, right? So positive or negative integers don't matter really. It's very easy to manage. Okay. Similarly, if you have rational numbers, okay. So in general, just add one extra bit. So in general, it turns out to store a number R, we need order log to the base 2 R bits. Okay. So this is important. When I'm storing numbers, I require, so the entries of A, B, and C, I don't require to store them. No, if I've got a linear program with a number 10 and a number 100,000, I don't require the size of my input to grow up by a factor of 10 to 100,000. I require log of 10 to log of 100,000. Okay. So this grows much slower than actual R. Okay. This is much, much lesser than O of R. Okay. It's much, much lesser, this thing. Okay. In fact, it's exponentially smaller. Okay. 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 So you don't require, so you don't use 7 bits to store numbers seven. Okay. Use 3 bits. Okay. Okay. So what do we do for rational numbers? It's not difficult. So for a rational number, let's say R is P by Q. What do we store? We store P and Q separately. Okay. We store P and Q separately using bits. So where P and Q are integers, right? Okay. So if I give you a number like 1.4142, I can store it at 14142 divided by 1000 or whatever and store them separately. I can even simplify them if I want and then just store bits separately. Okay. So dealing with this, so basically the point, I guess the only point I want to make here is for storing a number A, you require roughly log of A bits, basically. Is that clear? So my input, okay, so what's the input of the LP? So size of an LP instance, it's basically order of mn, the mn entries log 2 to the base u. So what is m? M is number of constraints, n is number of variables, u is the largest, is the magnitude of the largest integer entry among all integers values used in the rational representation of the entries of A, B, C. Okay. So I've got a matrix A, I've got a vector B, I've got a vector C. Okay. Each of this, there are rational numbers. Okay. If you want to think of them as integers for now. I've got integer numbers in each of them. I figure out which of these integers is the largest possible magnitude. Okay. I require log of that many bits to store it because everything else can be stored with fewer bits, basically. Okay. And if I've got rational numbers, whatever for every rational number, I'm going to use some integers to represent it. Whichever largest integer number I'm using, I require as many bits as that multiplied by m times n. Okay. So the point here is this should not depend on the entry A, B, and C, but log of A, B, and C. Okay. Is that clear? This is, I mean, if you're doing this for the first time, a bit of complexity. I'm not, yeah, I mean, it's useful to know this. So we want, so an algorithm runs in polynomial time for LPs. An algorithm runs in polytime for LPs if the worst case running time over all LP instances is polynomial in n number of variables, m number of constraints, and log of u. Okay, so this is what it means formally to be polynomial time for LPs. Okay, precisely. Okay, you have to be able to solve it. Of course, you have to solve the problem, and the running time should not grow exponentially in any of these parameters. They have to grow polynomially in all these parameters. If you can do this, then it's a polynomial time algorithm. Unfortunately, simplex doesn't satisfy this. In simplex, there are certain cases where the number of extreme points is exponential in the size of the problem, and you have to go through all the extreme points in the worst case. Okay. Any questions here before I go to ellipsoid method? No questions? Okay. So I will not do proofs for the ellipsoid method. I'm going to just give you the algorithms. Okay. But the idea is, obviously it says ellipsoid, which means you're using ellipsoids in the algorithm. Okay. So both the ellipsoid and the interior point methods uses some ideas from nonlinearity. It uses somehow, it's an LP, which is a linear class of problems, but it uses, in the ellipsoid method, it uses a nonlinear object to approximate the polyhedron. In the interior point method, we will work through the interior of the feasible region. So we're going to do different things. Okay. So I'll first describe the method for you, not for the optimization case, but for a related problem called the feasibility problem. Okay. So here is a linear feasibility problem. Okay. So it's a very simple problem. So let's say I've given you a polyhedron x in Rn, ax greater than equal to b. Okay, that's my I give you a, b, and I tell look at the set. So what is the linear feasibility problem? Given p, test if p is non-empty, and if it is not, and if test if p is non-empty, and if p is non-empty, sorry, test if p is, actually let's test if p is empty, and if p turns out to be non-empty, uh, find feasible x star in p. Okay. So it's a very simple, it's not the optimization version, it's a feasibility problem. Okay. I give you a polyhedron. Tell me, I give you a set of linear inequalities. Tell me if there is a point which satisfies its linear inequalities. If there is no point, that's fine, that's output. If there is, return to me a point which satisfies the inequalities. That is the feasibility problem. Okay. It is like what we do in phase one of simplex, except in phase one of simplex, we are trying to find a basic feasible solution. Okay. Yeah, I'm just trying to find a point in the set. Okay. Is that clear? Okay. So how can the algorithm look like? So maybe if you've got a polyhedron like this, it returns a point. So if P was, let's say, was non-empty, you have to return some point, okay, in the set. It could be any point. Or maybe P is empty. I give you a set of constraints for which there is no point. It somehow, there are logical inconsistencies and there's no point. It can be that a polyhedron is empty. So one of these two cases have to happen. Okay. Either one of this, it has to be able to identify and give me a point. Is it clear what the question is? Okay. So the algorithm actually uses, okay, so here's a key step of the ellipsoid method. Okay, there are lots of details, but for now, let's focus on the just on the broad algorithm. Okay. Okay. So first step, start with a large ellipsoid E naught that is guaranteed to contain P. Okay. So P could be empty. Okay. So if P is an empty set is a subset of every set. Okay. So you have to first find a large ellipsoid which is guaranteed to contain the polyhedron. Okay. I don't know. It can be a very large ellipsoid, but for example, in this case, that's an ellipsoid. Okay. And there's a formula for an ellipsoid, but there is some large enough ellipsoid which is known to contain the polyhedron. Okay. Okay. Next, what it does is it goes through an iterative process. So for k equal to 0, 1, 2, and so on till you terminate. Okay. Check if the center xk of ellipsoid ek uh, lies in P. Okay. Every ellipsoid is defined by a center. Okay. So for example, in this case, I've got a perfectly good ellipsoid. The center lies in this set. Okay. Okay. But it may not be the case, right? If I chose, for example, if my ellipsoid, let's say I chose a very, very large ellipsoid. Let's say my ellipsoid was something extremely large. Let's say this is my ellipsoid. It could have been that my center was here. This is not in the set. Okay. So it's a very large ellipsoid which contains the set. I don't know if the center lies in the set or no. Okay. So I will test. Okay. So if this is E naught, I test for X naught. Okay. Does it lie in the set or no? Okay. So either it's going to be yes or no, the answer. Right. So if yes, you're done. Okay. If yes, done. You exit. You solve the problem. Right. You're done. Right. You found a point which lies in the polyhedron. The polyhedron is not empty. Done. If no, this is where the work happens. If no, this is where the magic happens. Find a half space. Okay. So what's a half space? A linear inequality. A transpose X greater than equal to A transpose XK, where XK is the center, such that this polyhedron contains P. Okay. So what I'm going to do is, so let me go back to the figure. So I've got a center, I've got a point here, X naught, which is not in the center. So find me a half space. What's an half space? It's a partition of Rn into two sides with a linear inequality so that the polyhedron lies on one side of the set. Okay. So for example, in this case, this is a half space. A transpose X greater than equal to A transpose X naught. The polyhedron lies on one side of the half space. Yes. So what have I done? I've taken a big ellipsoid and I've cut it into two parts through the center, one side containing the polyhedron. Okay, now you have to create a new ellipsoid. Okay, next, find a new ellipsoid, EK plus 1, that contains the polyhedron intersected, I'm sorry, that contains the half space that contains basically EK intersected with this half space. Okay, this has to, okay. Okay, so what am I doing? If I go back to this figure, I want to now find a new ellipsoid which contains basically this half space. So this is a half space intersected with the ellipsoid. So that's basically this part of the region. Okay. I have to create a new ellipsoid which contains this. Okay. So my drawing skills are going to be tested here, but let me try to do it as best as I can. But here is an ellipsoid. Like, okay, so let me see. I mean, you have to just, my drawing will not be great. Okay, but let's try. Something like this. This will be EK plus 1. Okay, I've not drawn it perfectly like an ellipsoid. Okay, it should look like an ellipse. Okay, Okay. The idea is if this ellipse becomes much smaller in size, you have a big ellipse, it becomes a smaller ellipse, it becomes a smaller ellipse. Every time you're shrinking towards your polyhedron. If your ellipsoid area volume drops quickly enough, you should be able to quickly converge, hopefully. Okay, this was Kachan's idea. Okay, he's using a nonlinear body, basically an ellipse, to circumscribe the polyhedron. Okay, okay, okay. So, okay, so this happens. Okay, if the volume of ek plus 1 is too small to contain p, you're done with p being empty. Okay, so if your if your ellipsoid becomes too small to contain a polyhedron in it, okay, and this polyhedron has to be full dimensional, so it has to have volume. If the volume of the polyhedron, if the ellipsoid is too small to have a polyhedron contained in it, you can say that the polyhedron is empty. Somehow the volume has become too small to contain a polyhedron. Okay, else continue, go back and repeat. Do this step multiple times. So what this will do next is, in this algorithm, is it will now take the, in this case, maybe we are lucky and maybe we get in, or maybe we're not lucky. Maybe this is x1. So again, you create a hyperplane. Sorry. Yeah, you have to create a hyperplane which separates x1. Maybe it's not in this direction now, but the hyperplane might be in this direction. Half space. So this is now A transpose x greater than equal to A transpose x1. Create now an ellipsoid which contains this part of the region will be a smaller ellipsoid, and repeat. Okay, is the algorithm clear? Of course, the difficulty is to formalize this, to make all these steps algebraically possible. Okay, but is the concept of the algorithm clear? Any questions with the algorithm itself? Hmm? Okay, so there's some. Okay, so let me just. Okay, so I will just maybe. Okay, so let me just. Okay, so the first thing is we need to define what an ellipsoid is. Okay, so I won't do the proofs for this, but let me give you a little bit of sense of how you define an ellipsoid. So we require some objects for this. Okay, so one important object is this notion of what are called positive semi-definite matrices. This is a very important class of objects, and positive definite matrices. These will help you define ellipsoids. So I want to define these objects first. Okay. Okay. Actually, before I go, before I continue with this, I just want to check. Is the algorithm clear, or you want me to go through it one more time, or it's okay, or is it okay? Is it clear for you guys? Okay, fine, fine. Okay, then, okay, so we require this to define an ellipsoid, but more broadly, these matrices are very important class. And so let me first tell you what a positive semi-definite and a positive definite matrix is. Okay, so matrix D, so a matrix D uh, of size n by n, which is symmetric. Okay, so what is symmetric matrix? Ij entry is the same as Ji entry, okay, which is symmetric, is positive semi-definite, PSD, short form, okay? If x transpose dx is non-negative for every x in Rn. Okay. So it is positive definite if x transpose dx. So you create a quadratic function using the vector x. You take every vector x in Rn, you pre-multiply with x and post-multiply with x, you create a scalar number. You take the number, it has to be non-negative for every x. It's positive definite if, so this short form for PSD, positive semi-definite, positive definite if x transpose dx is strictly positive. Of course, if x is 0, this has to be 0. So this definition only is for all x in Rn, not 0. Okay. If I force x equal to 0, of course, this becomes 0. So this is okay. So equivalently, okay, and the way you write this is, so we say D is positive semi-definite. There's a notation which you use for this as D curly, instead of greater than equal to, you take a tilt. I don't know what it's called, but basically a curved form of this. Okay, and you say D is positive definite as okay. So if you want, you can think about it like non-negativity and non-strict positivity in Rn, but done over matrix spaces. Okay, but of course, this is not a simple operator because this has something to do with eigenvalues. Okay, so what it turns out, an alternative definition D is positive semi-definite if and only if all eigenvalues of D are non-negative, and it's positive definite if and only if. So by the way, this is a definition. Okay, so I'm okay. That's why I can use if. Okay, if and only if all. Okay, if and only if all eigenvalues are strictly positive. Okay, 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 and essentially when D is singular, when D is positive definite, okay, it turns out D inverse is also positive definite, and D is invertible. Okay, and the determinant. So essentially, it's invertible, and the determinants are non-zero. Okay, so a positive definite matrix is like inverting a number. Okay, if a number is positive, you can invert it. Okay, so it's like the corresponding form for matrix notations. Okay, okay, this is a very important class of matrices. Okay, there's a lot of work you can do with this. We will use it to define eigenvalues, but just as an example, you take a diagonal matrix. The eigenvalues of a diagonal matrix are just the diagonal entries. Okay, so this matrix is actually positive definite. Okay, you take a matrix like this matrix is not even positive semi-definite. Okay, clearly any matrix that is positive definite satisfies the positive semi-definiteness condition. Okay, so the eigenvalues of this are -1 and 2. This is not positive definite. It's not positive semi-definite itself. Okay, okay. So, but if you don't, but if you have a matrix like this, let's say 2, 1, 1, 1, the eigenvalues of this, you can check it. You can use any software, or for 2 by 2 matrices, maybe you know the formula for eigenvalues. It's just lambda. You don't have to know it, but you know how to find eigenvalues of a matrix. You do basically determinant of D minus lambda I equal to 0 and solve for this. Okay, so the eigenvalues of this are essentially non-negative. So this is a positive definite matrix. Okay, here is a matrix that is not, that is uh, the eigenvalues of this matrix. So these are eigenvalues. So the eigenvalues of this matrix are 2 and 0. So this matrix is positive semi-definite. Eigenvalues are non-negative, but it is not positive definite because eigenvalues are not strictly positive. Okay. Any, is that clear? I mean, have you seen positive semi-definite matrices before in some other context or no? It's very important class, okay? And it turns out it defines actually a class of convex optimization problems, which I'll also discuss later actually. Okay, so why is this important for now? Okay, it's a very important class of matrices. It's got lots of nice properties, but why it's important is it comes up naturally in the definition of an ellipse. Okay, so an ellipsoid. So what's the definition of an ellipsoid? So given Z in Rn and a positive definite matrix D and D positive definite of size n by n, and ellipsoid is defined as, okay, an ellipsoid, let's call this EZ comma, the center is going to be Z, D is sort of going to be a scaling matrix or scaling of the axis is given by, so here's the ellipsoid, X in Rn, X minus Z transpose D inverse, X minus Z is less than equal to 1. So it's basically defined by one single quadratic inequality, an ellipsoid. This is a quadratic function in X. When X is equal to 0, this this term will become 0. 0 is less than equal to 1. So X equal to 0 will satisfy this condition. As X changes, it will create a set. So for example, if Z is the zero vector and D is the identity matrix, this is simply the ball. So ellipsoid 0 comma I is just a ball in n dimensions. So it's what's called a hypersphere in n dimensions, or in this case, actually, it's just a unit ball. It's just x transpose x less than equal to 1. That's just a ball in 2D. In 3D, it's a sphere centered at the origin. Okay. If you change, so here's an example. So let's say Z is 1 comma 1. Let's say D is 2 1 1 1. Okay, you can find D inverse for a 2 by 2 matrix. You can find inverses. Okay, so if you write down ellipsoid Z comma D and you just plug in the formula, okay, it's x in R2 where x1 squared plus 2x1 squared minus 2x1 x2 minus 2x2 is less than equal to 0. Okay, so what I'm doing is I'm giving you a center, I'm giving you a matrix D. This matrix is positive definite. So you can find the you can find the inverse of the matrix easily. If you find the inverse and plug it back in here and just write down x minus 1 1, take this matrix, multiply, and just do the calculation, you will find it will reduce to this form. This is an ellipse. It's an ellipse which looks like this, ellipsoid. So ellipse is in 2D, ellipsoid more generally. It's an ellipsoid where the center is 1 1. Okay. And it's an ellipsoid. If you plot it, it actually looks something like this. It's something which is tilted. Okay. So basically, this matrix B does sort of essentially rotation. Okay. And Z is translation. Center is translation, D is rotation. Okay, depending on how the matrix D looks like, it might be elongated in one direction, it might be shifted in some other direction. It depends. So okay, so matrix D defines this. Okay, okay, and uh, uh, okay, okay. So let me just give you a theorem. Okay, we won't prove it. In the lecture notes, I've given you the proofs, but I won't be testing you on the proof for this ellipsoid part for this course. Okay. But in the lecture notes, I've given it to you. If you're interested, you can study it at your own time later. But I won't be testing you on this stuff. Okay. But let me just give you the theorem of the ellipsoid method. Okay. So here's the theorem. Okay. And okay. So given ellipsoid z comma d and half space. So this is actually the key result that helps with the ellipsoid method. Okay. So if I give you an ellipsoid, okay, I give you an ellipsoid centered at some z, and I give you a half space. Then let uh, let I'm going to define a new center. So this is a formula which I guess Kachian showed, building on other work. I define a new center and a new matrix D bar, which is going to define a new ellipsoid. Okay. So what is important here is the precise formula is not important. I mean, it's important definitely, but it's not important for us. What is important, I guess, is to see that the new center is defined by the old center and the the half space. So the Z and D and A, which defines a half space, defines a new center, Z, D, A, and N, N, D, A. Then two things happen. One, the new ellipsoid Z, uh, the if you take the original ellipsoid and you intersect it with the half space, it is contained in this new ellipsoid. Okay, which is that figure I showed you previously. I took an ellipsoid, I took the half space, I created, look at the intersection, that is contained in the new ellipsoid which I drew. Okay. Second, so that's the formula. Second, the volume of this new ellipsoid is e to the power minus 1 by, there's a formula for this, so let me just write it down. E to the power minus 1 by 2 into n plus 1 volume of the original ellipsoid. Okay, so there is a drop in the volume. This volume, so there's the original volume, it is decreasing. So remember, this number is going to be a number because exponential of a negative number. So this number will be less than 1. Okay, so it's some number which is less than 1. So it is shrinking the volume. Okay, so this fact that it is shrinking the volume, and it turns out this shrinking is fast enough for the polynomial time algorithm, is what gives you the ellipsoid method. Okay, so I will discuss this maybe a little bit next time. So next time what I'll do is on Friday I will just complete a bit more discussion on this. And one important thing that the ellipsoid method gives you is it actually tells you that some problems, I mean, just one thing I want to take away is if you observe something about the ellipsoid method, it is not using any property about the polyhedron itself. It's not using actually anywhere the inequalities defining the polyhedron. It says you form an ellipsoid, you find this hyperplane, okay, or this half space. So it turns out this actually has some very important implications for some linear optimization problems with exponentially many constraints. So we'll discuss that next time. It's called separation and optimization. I'll talk about that next time. Okay. But for now, I think I just want you to realize that there's a formula which tells you from a original ellipsoid and from a half space, you can create a new ellipsoid which contains the intersection of the old ellipsoid and the half space, and the volume shrinks. Okay. So the mechanics work out basically. Okay. Yeah. Is that a question?
No, but maybe so.
Go ahead.
The repeated volume of the ellipsoid and the optimal value will be the third point.
So right now there is no okay. So the question is optimal value. That's a good point. I've not told you anything about optimality. Right now, I just want to find a feasible point. So we can translate the optimality problem to a feasibility problem. We'll discuss that later. Next class, I'll tell you.
Yeah. Right. I mean, the idea between this is the point in which the first time is
The center of the ellipsoid is in the polyhedron. You're done.
I mean, under the steps.
Yes.
First time the polyhedron lies in the ellipsoid will be the optimal.
Yes. Okay. But how do you know the polyhedron lies in the ellipsoid? The center of the polyhedron. So everything is done with the center of the polyhedron. So the moment the center of the polyhedron lies in the ellipsoid, you stop. Yeah. Yeah.
I
You're right. Yeah.
mean,
How do you solve?
this method
For
find the optimal.
Okay. There's no optimality here. Okay. So
You can
yeah. So one way you can think about optimality is very simple. Suppose, okay, if you don't mind, I'll just take 1 more minute. One way to think about optimality is very simple. Think about LPs. Primal, dual. Okay. What is optimal? X is primal optimal and P is dual optimal. What do you require? Primal feasibility, AX greater than equal to B, dual feasibility, and complementary slackness or strong duality, which you can write in many ways. One way to write it is C transpose X is equal to P transpose B. The two objective functions match. This is a set of linear constraints, linear feasibility conditions in X, P. So if I can solve these conditions, I solve my optimization problem. So I can think of optimization as a feasibility problem in the primal dual space, basically, from strong duality. So if I could just take the ellipsoid method and apply it to this problem, this is my polyhedron defined by A and whatever, all these things. These are linear conditions. So if I apply feasibility to this problem, I solve the ellipsoid solves the LP problem with it. But you don't have to go to primal dual space actually. Okay. Yeah. Is that clear? So you can take a optimization problem and think of it as feasibility problem, except you use the dual variables and use dual feasibility and use strong duality. So I mean, this is why duality is key to everything basically. Okay. Okay, let's stop here.